what up, Alice? Well, let's get this party started with some physics. And I'm just going to do example problems for you. Sound good? So I think this would be a good one right here. Oh, yeah, here's a good one. The ice block. Let's do it. Okay. The ice block. A 6 kilogram. Did they close the door? 1 second. Tell me. All right. The ice block. You got a 6 kilogram ice block that is acted on by two forces, F1 and F2. The magnitudes of F1 and F2 is 13 and 9, or 11. Find the acceleration of the ice. Okay, good. So, we have a block of ice, and its mass is 6 kilograms. Can you see that, Alice? You can read the board? All right, good. All right, so its mass is 6 kilograms, and according to the picture, this kid is pushing on it with a force of 1, which is 13 newtons at an angle of 60 degrees from the horizontal. And this kid is pushing backwards on it at a force 2 of 11 newtons at an angle of 30 degrees with the horizontal. If you want to see the picture, here's what it looks like. It's this one right here. Got it? All right. What other forces on it? Well, there's one more force that's on it, and that would be what we call the normal force. Okay? And that's the force that, imagine if you're the ice block, what do you feel pushing onto you? Actually, there's one more force that I'm missing here. Can you see it? Can you tell me what it is? This is the one I made a big deal for you to say. You need to say this correctly. W, exactly. It's the weight of the block, which is actually equal to m times g. So since we have m, we can calculate the weight. We just multiply it by g and we're good. So I have 4 forces acting on this block. Cool? There's the normal force, the weight, the F1 and F2. The normal force is the force that the floor is pushing up on the block. Because if you look at it, there's a force going down, and these 2 forces are going down. If this normal force weren't here, then this block would just be pushed down, wouldn't it? But this normal force, or responsive force, is responding to all of this force pushing down. And we know that when I'm pushing a block on a table, this thing is not going through the table. So there must be some counter force pushing up on it to balance out both the weight and the y components of these 2 forces. Now notice how I said immediately the y components. So you see a vector, you see a force, you break it up into its components. That's just what you do without even thinking about it. So in this case, before I even start the problem, I'm going to break this guy and this guy up into their x and y components. Is that all right with you? I'm going to make F1. Here will be theta. So this will be F1x, which is F1 cosine of theta. And this one is F1y, which is F1 sine of theta. Are we all right with that? All right. This F2, I'm going to immediately break up into its components. F2x is F2 cosine theta, and F2y is F2 sine theta. I am going to probably change this to a phi. Or maybe I'll do this. So what I did here, and I don't know if you can see that on the computer close, maybe is that better? What I did was I put a little 2 on the bottom of this theta right here. So it's theta 2. And I put a little theta 1 over here. So this tells me this is angle 1 and this is angle 2. Cool? All right. So now I'm going to, well, I'll do a coordinate system. That's always a good thing. Now what I'm going to do is I'm going to add up the components in the different directions. And in this case, here's what I want to do. I want to figure out what the acceleration is equal to. Actually, there's a good question. What I usually do is I usually do some of the forces in the x direction, and I also do some of the forces in the y direction. But I want to find the acceleration. So which one do I do? The x direction or the y direction, or both? The x direction. Why not the y direction? How come? You're absolutely right. I'm just wondering, how did you get that? Very good. Because in the y direction, this mass times acceleration in the y direction is going to equal to 0 because there it's not accelerating in the y direction. It's on a table, and it's not going up or down. It's going right or left, depending on which person is pushing harder and depending on the angle, of course. You guys get it? You get it? So, well, obviously you get it because you're the one who told me the answer. So I'm only going to do some of the forces in the x direction because summing the forces in the y direction won't tell me anything about the acceleration because all the acceleration for this problem is going to be in the x direction. All right, let's add up the forces. Which forces, tell me some forces that you see on this board that are acting in the x direction. Angle 60 and angle 30. I think what you mean is F1x. It's this force is acting in both the x and y direction, but specifically the x component of it is the one that's acting in the x direction. So F1x and F1y. Besides that, the weight is going straight up and down. The normal force is going straight up and down. Those aren't acting in the x or y, so I'm not going to include those. So it's F1x minus F1y equals mass times acceleration in the x direction. I apologize if that's hard to see. My pen is starting to go crappy. Let me see if I can go find a better pen. While I find a better pen, can you figure out why I have a minus F1y there? So what's your response? How come I have an F1y? A negative F1y? No, it's not because I'm getting rid of the y direction. It's because, I'm sorry, that is terrible. The reason why you can't answer it correctly is because I screwed up in putting it up right. So it's a negative F2x. There's a positive F1x, but a negative F2x up there. Well, I'll tell you why, since I screwed it up. It's because F2x is going to the right, whereas F2y is going to the left. There we go. So I just plug in F1 cosine of theta 1 minus F2 cosine of theta 2 equals m times ax. And if I want to figure out what a is, all I got to do is divide by m. So that's my answer. And you can plug in numbers if you so choose. This one is 13 cosine of 60 minus 11 cosine of 30 divided by 6, and that's going to give me my acceleration. And if I plug in the numbers, I'm going to get ax equals negative 0.5 meters per second squared. We're cool? What does that mean? Who wins in this game of push-a-war? I call it tug-of-war if they were pulling, but since they're both pushing on a block of ice, who's going to win? Student number 1 or student number 2? Student number 2. And the reason for that is because the acceleration is a negative number. So the computer is telling, or the physics is telling you that since your acceleration is a negative number, it's accelerating that way. That means that even though this guy's pushing with a force of 11 newtons, and this guy's pushing with a bigger force of 13 newtons, he's pushing at a smaller angle, which means more of his x component contributes to pushing in the x direction than this guy's does. This guy is really only pushing the thing into the table. He's kind of wasting all of his force that he's using. Does that make sense? All right, cool. The next question, part B of the question, is what is the normal force? What is N equal to? Now, normal force is in the y direction, so it would behoove us to say, okay, well now let's do the sum of the forces in the y direction. First thing, before we plug in all of the y direction vectors that we see, we want to find out, well, what is the acceleration in the y direction? No, it's not gravity. If it were gravity, it would look like this. Is this thing falling? No, there's a table. It's on a table. No, its weight is not its acceleration in the y direction. It rhymes with my favorite character from a popular movie with Baymax. Rhymes with the name of a popular character in my favorite movie with Baymax. Do you know what I'm talking about? No, you don't. Nope. All right. The main character in Baymax, or the Big Hero 6 was a kid named Hero, and so the answer for the acceleration is 0. Very good. Right, it's 0. It's not going up. It's not going down. It's on a table. Even if it's sliding right and left, in this particular case, it's sliding to our left. Even though it's sliding left, it's not accelerating anywhere in the y direction. Remember, because I'm asking you specifically, what is its acceleration in the y direction? It's 0. Does that make sense? All right. What forces do you see acting in the y direction? There's 4 of them. I want you to tell me all of them. Not only do you got to tell me the force, you got to tell me if it's plus or minus. Because I've done my assessment of the right-hand side of the equation. Now I'm going to do the left-hand side. So now I'm adding up all the forces. Come on, what forces are there? There is the mass, negative mass, positive n. Okay, mass is not a force. The weight is a force, and I agree with you, it's negative. So it's negative W Come on, I told you I would kick you in the head next time you do that. There you go. All right, and then positive n plus n, I agree with you. Okay, what other forces do you see? If you don't know, say IDK. That way we can keep moving. All right, remember, even though this is F1 and F2, this is acting in both the X and Y direction. We broke it up into its components so that way we could see it better by doing this, and then immediately we can say, this force is acting in the Y direction. It's also acting in the X direction, but it is acting in the Y direction, and this is exactly how much of it is acting in the Y direction. So I should include this number right here. And it's negative because it's pushing down. So it's minus F1 sine theta 1. You get it? And then the other force that's acting in the Y direction would be the Y component of force 2, which is actually written right here. So it's minus F2 sine of theta 2 is equal to 0. Now I wanted to solve for n, and luckily in this case, it's really easy. All I got to do is put everything that doesn't have an n onto the other side. I'm just going to throw it over there. So I've got n equals to the weight plus F1 sine theta 1 plus F2 sine theta 2, which is 6 times 10 plus 13 sine of 60 plus 11 11 sine of 30. Plugging in those numbers. Oh wait, there we go. Actually, I didn't plug in those numbers, but that's all you do. You just plug those numbers into a calculator. What is the second question? Oh, I see. Wait. Find the normal force exerted on it by the table. Normal force is equal to that plus that. Oh, I see. Wait a second. Here. This is what I'm screwing up. I did calculate it out. It's 75. Okay. You just plug the numbers into a calculator, you get 75. Imagine I took away the people out of this equation, out of this scenario, okay? What would the normal force be then? You can almost see it immediately. What is the weight of the box as measured in newtons? That was a teaching opportunity. I should have just said, what is the weight of the box? Good. I was waiting for you to say 6 kilograms, and I would have been really upset. Because that's not the weight of the box, that's the mass of the box. In order to get the weight of the box, you're going to need to multiply that by 9.81. Let's just round that off to 10. So let's say that the weight of the box is 60 newtons. Are we cool? If you had a block of ice sitting on a table and it's pushing down onto the table with 60 newtons, then the table is pushing up onto the block with what force? With 75 newtons? No. I'm saying pretend we didn't have these people here. If the only two forces involved was this downward weight and this upward normal, then the downward weight would equal 60 newtons pushing down, and the upward normal would equal 60 newtons pushing up. If they were imbalanced, like one was going down at 60 and the other one was going up at 75, then the block would start floating into the air. We know that's not the case, so we know they have to be balanced out. We cool? Now, let's add the people back in. Now we have this push-a-war game going on. Weird craziness thing. Why is this thing ramped up? It went from 60 newtons, which was before we had the people, to now it has 75 newtons. Why does the table now have to push even more than just the weight of the block of ice? I'll tell you why. I mean, we just don't have time to keep. Right, exactly. Because the table is compensating for the extra force, the y component that this kid is pushing on it, and the y component that this kid is pushing on it. Does that make sense? So the weight of this block is still 60 newtons. It's still 60 newtons. That's the weight of this block. It's 9.81 times 6. Close to 60. But the normal force is bigger because it's responding to the y components of these kids pushing down on the table at it. And if they didn't break the table, then we're assuming that the acceleration is 0. And so your mass times acceleration is 0. You've got kind of a balanced situation going on. So in turn, your normal force has to respond with a bigger force. I hope that makes sense. We good? All right, good. Let's do this one. And this one actually has hard geometry in it. I think that I've covered a geometry like it with you before, but it's kind of tough. So let's do it. All right. Alice, you're in my Algebra 2 class. Have you had geometry yet? I feel like this could be I feel like this could be a tough geometry problem. So let me explain this as best I can, because I think this is a really good problem. Okay. You're going down a skateboard on a ramp. So here's Alice. And you're going down a skateboard that's on a ramp. The ramp is at an angle of theta. Cool? You have a mass of m. I dare not ask you what your weight is, so I'm just going to say m. Because I'm a gentleman and I don't ask girls how much they weigh, so I just say, oh, your mass is m, and it can be whatever it is. Actually, technically, I didn't ask you how much you weigh. I put your mass, which is m. If I wanted to get your weight, I would say your weight is m times g. We cool? Okay. I think I'm going to mess with this picture a little bit, so I'm just going to draw it a little bit bigger to give myself some room. So your weight, which goes down, it goes mg like that. Are we good? Now, the normal force pushes in what direction? Does it push directly up? Does it push to the right? Does it push up and to the right? Does it push down to the left? Down and to the left? Which direction does up and to the left? So you're saying here. Or is that the wrong left? It doesn't. It doesn't push that way. It actually pushes this way. It pushes perpendicular to the surface that it's on. Because what is the normal force? The normal force is the ground pushing on the object that we're talking about. And if the ground is at an angle like this, then the normal force is going to push up from the ground that it's on, but the ground is slanted, so the normal force is going to be perpendicular to that. Does that make sense to you? Now it does. Okay, cool. All right, here's where it gets kind of crazy. I haven't taught this to you, but I could. There's another force involved. I'm going to call it F little f. It stands for force of friction. I think we don't get into force of friction until we talk about chapter 9 or chapter 6, but it would be there. Are we cool? Here's the crazy part about it. Do you like breaking vectors into their components? Oh, by the way, I forgot to ask. The acceleration of this object, of you sliding down this ramp, is it going to be up, to the right, to the left, down, down and to the right, up and to the right? What do you think? Up and to the right. So you think that this person is going to be going accelerating that way? Oh, no, 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 no. This person's going to accelerate that way. They're going down the ramp. How am I going down a ramp and all of a sudden I'm flying up into the air? Does that make sense? Their acceleration is going to be going down at an angle like that. Okay, all right, here's the thing. Do you like breaking up vectors into their components? Not really. I agree with you. I completely agree with you. Here's the problem. We have to break this, this, and this into its x and y components. Do you see what I'm saying? The only force that is going in an x or y component only is this one right here. But this force, and that acceleration has x and y components. I hate x and y components. I would rather make it so it's easier. So one of the tricks that I can do, and you saw me do this a little bit in chapter 2 when we were talking about projectile motion, is one of the tricks I could do is this. Let's see, wait a second. All right, so what did I do? Can you see? Can you respond? What did I do? Because I fixed it. I fixed the problem here. Are you completely confused as to what I did? All right, well, what happened to the computer screen? Or the camera, at least. It's tilted. Yeah, all I did was I lifted up one side of my computer. But look, if I were to take my coordinate system and I were to tilt it just a little bit, then I could make this thing be completely horizontal, right? And I could make this thing be completely vertical. I'll show you. There. Now, the force of friction and acceleration is completely horizontal. And the normal force is completely vertical. Your whole world is tilted, that's true, yes, I agree. But as far as the things we're concerned about it, those are completely horizontal or completely vertical. Do you see it? The only thing that is slanted, the only force that is slanted in this picture right here is the W. So what we're going to do is we're going to take our x and y coordinates, which is like this, and we're going to change it. We're going to take it and we're going to slant it this way. Because that will make all of the math way easier. In fact, not even way easier, but possible to do. The only trick here is to make sure that we know a little bit about our geometry. Now, since you've had geometry before, I'm going to kind of go through this a little quickly. All right. I think I want to cover this side of the board. Okay. So, I guess what I'm asking is, if this is theta, then what is this? If this is theta, what is this? No, you don't need sine and cosine. Is this theta right here? If this is theta, then what is this? Come on, think about your properties of a triangle that you've had before. Okay, all right, fine. Here. I'll do it like this. I'll draw it. Well, would I be able to argue with you to say that this question mark is equal to 90 minus theta? Because if I were to add up all of the angles in a right triangle, they would add up to 180. This part right here counts for 90 degrees of that. So this is theta, then whatever that is 90 minus theta. Are we cool with that? All right. What is this angle right there then? If this is 90 minus theta, what is that? The same as the angle. Yeah, it's theta. Are we cool with that? So, if I were to take my coordinate system and shift it like this, then this would be on the y-axis. This would be on the x-axis. This one would be at an angle. And what angle would it be at? Well, it would be at angle theta over here. Does that make sense? okay? That means I need to break the W into its x and y components. In this case, I'm going to call this Wx, and I'm going to call this Wy. Because this W is pointing a little bit down and a little bit to the right. Now be very careful with this. What is Wx and what is Wy? This is that sine and cosine deal. If you don't know, say IDK, and we can keep moving. Oh, come on, you can do this one a little bit though. All right, we'll keep moving then. My question is, what is Wx equal to? I'll give you a hint. The answer is either W sine theta or W cosine theta. You have to figure out which one it is. W cosine theta. Okay, okay. Wrong. I'm not going to burn you too much for it being wrong, but it's W sine theta. The reason why I'm not going to burn you too much is because it's not an easy question. So Wx in this case is W sine theta. I think the reason why you said it's W cosine theta is because whenever we're talking about the x direction, we usually say W cosine theta. Cosine theta is usually attributed to the horizontal part, right? But then again, usually I define the angle theta to be down here. In this scenario that we're playing out, I'm defining the angle to be up here. So my Wx, this one, also known as that one, is W sine theta because it's the opposite side. Remember, I told you, the opposite and adjacent sides change depending on how you define the angle. For some reason, usually we define the angle to be between the horizontal and our angle. But in this case, we're defining the angle theta to be the one on top. Does that make sense? And I've taught you this before. You know how to do this. Okay. So Wx is equal to W sine theta. And Wy is equal to W cosine theta. All right. I'm going to erase this. So I want to figure out what is the acceleration. What's the acceleration equal to? Okay. Well, the acceleration is equal to sum of the forces in the x or the y direction. Are you accelerating in the x or the y direction? In the x direction. Very good. Now, I didn't teach you about force of friction, and besides the fact that we're on a skateboard, so there is no real friction involved here. It's almost like you're sliding down or gliding down or whatever. So I'm going to erase that force of friction thing because I didn't teach it to you yet. What forces do you see acting in the x direction? Acceleration? No, acceleration is not a force. Acceleration is an acceleration. What forces do you see that I drew up on the board here is acting in the x direction? Remember, the x direction is going slanted like this. Are there any lines on this drawing that I have going slanted like this? Or actually, I shouldn't say lines, I should say, are there any arrows pointing in a slanted like that direction. It could be going up or it could be going down. The Wx. Do you see any other forces acting in the x direction? This isn't the force. That's why I drew it with a squiggly line and I didn't draw the arrow on the person. I just kind of do a squiggly line to kind of indicate it's going in that direction. Oh, okay. I can erase it because it's not really pertinent to our problem. Okay. But there aren't any other x direction. If the force of friction thing was still there, then I would put Wx minus the force of friction. But it's not. It wasn't there. Because we're sliding down this thing almost at frictionless. Okay? So Wx is equal to W sine theta. Oops. W sine theta is equal to mass times acceleration in the x direction. W is m times g. Mg sine theta is equal to mass times acceleration in the x direction. And m cancels out with m, and so you end up getting that acceleration is equal to g sine theta. You plug those numbers in. Actually, I didn't tell you any numbers, so you're done. Does that make sense? Now, if theta equals 0, what would your acceleration be? What is the sine of 0? Use a calculator. Okay, sine of 0 is 0, so multiply that by g, you still get 0. If theta equals 0, your acceleration would be 0. Does that make sense to you? Think about this. I can change theta. I can make it a steeper or not as steep hill, right? If I made theta to be 0, what kind of ramp would I have? A pretty lame one, I would say. In fact, I would actually venture to say that you're standing on a theta equals 0 ramp right now. It's flat ground, horizontal ground. So how fast would you be accelerating on a skateboard? You're not pushing or anything on flat ground. What? You'd be accelerating 0. I wouldn't be going anywhere. I'd be, okay, ready? Let's start the experiment. Go. Does that make sense? All right, let's try this one. If theta equals 90, what would acceleration be equal to? Use your calculator. What is sine of 90 degrees? Sine of 90 degrees is 1. So what is 1 times g? It's g. So you're telling me that if theta equals 90 degrees, then my acceleration is g. Does that make sense to you? Yes or no? Does that make sense to you? In this case, no. Okay, all right, here. If theta equals 90 degrees, then that would basically be equivalent to me taking my skateboard on, let's say the Empire State Building. I take my skateboard, I put it up against the side of the Empire State Building. I go to the roof, I lean over, I put my skateboard so that the wheels are touching the side of the Empire State Building, and I jump on the skateboard. How fast would I fall? Or I guess my question is, how fast would I accelerate? I'd accelerate at exactly gravity. Are you kidding me? It'd basically be like jumping off the Empire State Building, but this time you have a skateboard on your feet. Does that make sense? If I made the angle to be 90 degrees, I would fall down this thing at gravity. That's all I would do. In fact, most of the time my skateboard wouldn't even touch the wall of the thing. I'd think that, like, I'd basically be falling at gravity because all I have is a skateboard up against the wall. It's not really it's not slowing me down any. You get it? So the physics, the math teaches you stuff about what makes sense in the real world. What my favorite thing to do is to take this math and then all of a sudden apply, like, does this physically make sense in the real world? If theta equals 0, it would make perfect sense my acceleration is 0, because I'd be asking myself, how fast would I be sliding down a ramp that is horizontal? I would be sliding, I wouldn't be going anywhere. And then I ask, if theta equals 90, what does that mean? Well, that's essentially me going on a ramp that is 90 degrees. That's basically me trying to ride down the Empire State Building or some tall building or whatever. All I would do is just fall flat on my face at an acceleration of gravity. With a skateboard attached to my foot. We cool? I want to do one last thing with you because I think it's important. But this is pretty much it. Let's find the normal force. So I'm going to add up all the forces in the y direction is equal to mass times acceleration in the y direction. In the y direction, the acceleration is 0 because this person is going down the ramp in the x direction, but in the y direction, I'm not going up and down off the ramp. Adding up all the forces that I see in the y direction, I see a normal force, which is a positive number, but I see a negative w cosine theta equals 0. Because the right-hand side of that equation is 0. If I want to solve for n, I simply say that n is equal to w cosine theta. And that, my friend, is that. So the point I guess I was trying to make is, this is a hard problem. What makes it hard is this concept of shifting your axis, changing it so that in a way it better suits the needs of the problem that we're doing. So I turn my axis a little bit at an angle so that way I can align this normal force in the direction that I'm accelerating at to go along those components. And that messed with one of my my traditionally vertically thing and turned that into something that's a vector. But I'd rather have that than have to break the normal force, the force of friction, the acceleration all into their components. I'd rather do one of them than three of them. Does that make sense? Can I ask one last question? If theta equals 0 in this case, what is the normal force equal to? And what does that mean? All right, if theta equals 0, the cosine of 0 is actually 1. So that's saying the normal force would equal to the weight. Does that make sense to you? And I feel like it does. Because remember, in the case where theta equals 0, we're talking about a horizontal surface. Are you sitting in a chair right now? Okay. Imagine this chair is a big skateboard. What is the force normal that is the floor is pushing on your wheels of your chair or skateboard or whatever it is? It's equal to W. It's equal to whatever your weight that you're pushing down with the floor is. There we go. Now, if you were on a ramp, the floor would actually push down less than your weight. And one way to confirm that is to say, all right, well, what if theta equals 90? The cosine of 90 degrees is 0. And so you're saying that if I'm falling off of the Empire State Building, does that mean that the wall of the Empire State Building doesn't really push onto my skateboard? No, it doesn't, because all your direction is going in the y direction. Or, I guess in this case, it's the modified x direction. All right. Anyway, I got to go. So I'll talk to you later. I hope this made sense.